Greetings from the Department of ECE, SJBIT. Today we are going to look into the second part of Module 3, which is strip lines. In the previous session, as we have discussed about the microstrip lines and the characteristic impedance, effective dielectric constant derivation of microstrip line and the losses associated with it. These three topics were completed in the previous session. Now in this session we'll look into the other three topics, which is parallel strip line, coplanar strip line and shielded strip line. So if we look into the parallel strip line, as I have told you, all the strip lines configuration will be, you will have a dielectric material, then you will have a top layer conductor and bottom layer. This is the geometry of a parallel strip line. One can notice that you have a dielectric material which is separated by conducting material on the top layer, placed on the top layer, and the conducting material which is placed on the bottom layer, acting as a ground plane. So the width of the dielectric material, or the height or width, which is represented as d, and the dielectric material will have parameters like epsilon r, and that is a relative dielectric constant of the slab, epsilon rd. And the definition of a parallel strip line is, it consists of two perfectly parallel strips. That is, this is a first parallel strip and this is a second parallel strip. Two perfectly parallel strips which are separated by a perfect dielectric slab with uniform thickness, as it is shown in here. The width of plate width, if I consider, this width is considered as W, and the height of the dielectric substrate is considered as HRD, and the relative dielectric constant of this material is considered as epsilon RD. Coming to the characteristics, few more characteristics of this parallel strip line are distributed parameters like the inductor, capacitor, resistance and conductance. As we know that in a transmission line, the parameters are no longer lumped, they are distributed along the transmission line. So in a microwave integrated circuit, the strip line can be easily fabricated on a dielectric substrate using the printed circuit technology. That is a major reason why strip lines are preferred in MMIC or MIC circuits. The parallel strip line, which is similar to two conductor strip lines, as we know that acting like a capacitor, two parallel strips separated by a air or as a dielectric medium acts as a capacitor. In the same manner, even here you have two conducting layers which is separated by a dielectric, and this parallel strip line supports quasi TEM mode, TEM indicating transverse electromagnetic waves. So in a TEM wave, when it is propagating in positive z direction, TEM meaning, as you know that suppose if I have electric field, magnetic field and the wave propagation, all three are perpendicular to each other. So electric field, if it is in this direction, H is in this direction, then the wave propagation, direction of propagation is in this opposite direction. All and we are considering that lossless strip line, lossless indicating there are no losses. The losses associated with the strip line are represented by resistor and conductance, resistor in series, resistance in series and conductance in parallel. So as it is a lossless, if I am considering for a lossless, then R and G must be made equals to 0. Then as we know that if we have a width W much larger than the separation distance, the fringing capacitance can be neglected. Now we'll have a equation for an inductance between along the two conducting straps, mu A by D. Similarly here, as we know general formula mu A by D, that can be represented here as mu is permeability and D is the distance between, that is the height of the dielectric substrate, and W is the width of the dielectric substrate. Similarly, as you know that it acts like a capacitor, the capacitance between the two conducting strips epsilon A by D, which can be represented as epsilon is permeability, A in this case it is width of the and D is the separation. Then now coming to, suppose if it is not a lossless or lossy one, then R and G can't be neglected. You can represent that R and G values as 2 into RS by W, where RS indicating skin resistance or surface resistance. Then G can be represented as sigma omega by D, sigma indicating conductivity. Now, why we have considered all these parameters like R, L, G, C? These are distributive parameters. When it is a lossless, these two will become 0. If not, all these 4 will be considered. Majorly, we have considered this to evaluate the characteristic impedance. The general formula for a characteristic impedance is square root of Z by Y, where Z indicating series impedance, Y indicating shunt admittance, which is R plus J omega L, Y is G plus J omega C. When it is lossless, R and G will become 0, Z0 will become purely constant, which is root L by C. Now substitute the value of L and substitute the value of C in this equation, results in this, where mu naught by epsilon naught, if I replace that with the free space impedance as 377 ohms, then you can consider the Z0 value or evaluate the Z0 value by using this expression. And the phase velocity, already as we have defined, velocity with which the wave travels in a media, which is represented as omega by beta. If you express in terms of root LC, substitute L and C values, you can represent in this manner, or you can find out Vp value, that is velocity of propagation, you can calculate from this equation. Suppose if the characteristic impedance of a lossy parallel transmission line, if I want to represent, considering this approximation, Z can be found out in this manner. Same way as we have seen in case of microstrip line, even this lines you'll have losses, like all these 3 losses, as we know: attenuation loss constituting 2 losses. One is dielectric loss and conductor loss. Next one, radiation loss. Coming to this attenuation losses, we'll have alpha C and alpha D. Alpha C representing conductor loss and alpha D representing dielectric loss. So this how can we evaluate? Means from the propagation constant. From propagation constant of parallel strip line or a 2-wire parallel transmission line, as we know that, which is square root of Z into Y. Z is R plus J omega L, Y is G plus J omega C. By considering this condition, you can represent gamma as this. From that, if you separate constants, means like alpha and J beta, we know that gamma can be represented as, it is a complex quantity. It can be represented as alpha plus J beta, where alpha indicating beta indicating phase shift constant, alpha indicating attenuation constant. So by comparing this with this equation, comparing these two, one can find out alpha and beta value like this. Then alpha, which is constituted due to both dielectric loss and the conductor loss, so which we have considered, which we can evaluate by using this expression. Now coming to the next type of strip line, which is nothing but a coplanar strip line. The structure, if you observe the structure of a coplanar strip line, you will have a dielectric material which is having the 2 conductor strips which are placed on the top of the dielectric substrate, and one of the strip is considered or is connected to ground. So this will act as a ground, and the other conducting strips which will act for transmission of signals. So each width is conducting strip is considered as W, and the separation between the conducting strips considered as S, and the height of the dielectric substrate considered as D. Relative permeability and permittivity of the dielectric material considered as mu D and epsilon D. So by looking at the schematic, one can notice that it has two conducting strips on one layer of the substrate, and with is connected to ground. So it is over a conventional parallel strip line, because the two strips are on the same side or on the same substrate surface, and it is very convenient for giving connections. So in MICs, the wire bonds have always presented reliability and reproducibility problems. The coplanar strip lines, to some extent, they can eliminate the difficulties involved in connection point. That is the shunting elements between the hot and ground strips. So reliability can be increased, reproducibility is enhanced, and the production cost will be decreased. So as we know that major parameter which we will look into in all the strip lines as characteristic impedance. Major reason why do we need means to match the impedance with the input signal, you need to you need to know about the characteristic impedance, else you will have losses. So the characteristic impedance we can evaluate as average power 2 into average power by I naught. General formula, like as we know that average power equals to P is equal to I square R. So I square into Z naught, and this 2 divided by 2 factor which you are getting due to conversion. So if I know that peak current value, you can evaluate Z naught, and you can evaluate the average power based on electric and magnetic field intensities which are given in the problem. This is about the coplanar strip lines. One can notice here the geometry, then the characteristic impedance, then the silent features of it. And if you look into the problem, a small problem, so they had given you the average power, P average value is given to you, which is 250 milliwatts, and the peak current also is given to you, that is I naught is also given to you, 100 milliamps. You have been asked to determine the characteristic impedance. The formula just now, as we have seen, Z naught is equal to 2 into P average divided by I naught square. P average known to you, I naught known to you, just substitute, and if you evaluate, you will get the value of characteristic impedance as 50 ohms. Now coming to the last one, which is a shielded strip line. The geometry is slightly different from the previous ones. It has a and has its strip conductor which is embedded in a dielectric medium with top and bottom ground planes which have no connection. You can observe here, top layer and bottom layer both are ground plane, whereas the strip is embedded with media. So if I consider the height of the dielectric media material as D and epsilon r as the permittivity, then a strip conductor of width W which is embedded with substrate. So this is about the characteristic impedance variation with ratio, that is height ratio as a parameter. So if it keeps on, that is this one, W by D ratio, and this indicating Z naught. So Z naught value variation, if W by D ratio or T by D ratio, if you vary, how it varies one can notice here. It keeps on decreases. If you increase, it keeps on decreases. So now you can find out the characteristic impedance of a wide strip microstrip line, that is a shielded strip line, that is wide strip indicating it should satisfy this condition, that is W by D ratio must be greater than 0.35. If it satisfies this condition, then one can evaluate the characteristic impedance as 94.15 divided by square root of epsilon r into r 1 divided by W by D into K plus CF by 8.854 into epsilon R, where K can be evaluated as 1 by 1 minus T by D. D value, if it is known to you, you substitute here, you can evaluate K. Now coming to this W value, D value is known to you, CF you need to evaluate here. So CF can be evaluated from this expression, which is 8.854 into epsilon R divided by pi into 2K into ln of K plus 1 minus K minus 1 into ln of K square minus 1. So where CF indicating it is a fringing capacitance, the capacitance which is occurred due to the electric and magnetic fields which are traveling in the air. Okay, so with have completed the 4 different types of strip lines. In the previous session only we have covered this. In this session we have covered all these 3 strip lines: parallel strip line, coplanar and shielded strip line. So with this first part of module 3, which is strip lines part, is completed. Thank you.